Differentiation Mobile, quality e-learning experience on the go.
Hello and welcome back to the class. Our topic this time will be considering differentiation of algebraic functions. Differentiation of algebraic functions. Right. Okay, and for this topic we'll be considering differentiations from first principle and some basic standard derivatives, rules for differentiation of sums and differences. Okay, and so we'll keep off by first principles and we'll be using illustrations. We're talking of differentiation by first principles. Alright, we'll be using examples to illustrate this. Alright, by first principles, if you are given a value y equal to 2x squared plus 5, okay, and you are told to differentiate this value, alright, all you have to do is this. You have to take out some, you have to add some change to x and y, and then you differentiate. That's by the way. I just want to say some other thing before we continue. Alright, I want you to know that the derivative of a constant is equal to 0. Let me state these rules. The derivative of a constant, that is when a constant is differentiated, it will be equal to 0. Okay, and so having said this, we can carry on with our topic on derivative. And so we continue with our examples. The example above, we have y equal to 2x plus 5, 2x squared plus 5. Okay, and so by first principle, the first step is to add a little change to y. Okay, and remember that since it's an equation, a little change to y will affect or will affect a little change to x. Okay, alright, and then all squared plus 5. Observe what I did here. I added a little change to x and not to 2x, because x is a variable, and since the change in the variable of y will as well lead to a change in the variable of x, and so we have this. Alright, 5 has no variable. I would have added a change had it been it had one. Okay, so the next step, the first step, step 1 says you add a little change the y and the x to x and y variables. Okay, and so you have this. Alright, and step 2, we have to carry out some simplifications. Simplify the expression. And so when we carry out some simplification, we have y plus dy is equal to 2 into x plus dy. Okay, this is x plus dy again. Okay, because that's squared, you're seeing on top there, plus 5. Okay, and so y plus dy is equal to 2. X times s gives s squared plus 2x dx. Okay, and the plus dy all squared, sorry, plus dx all squared. Alright, this is dx. Okay, alright, and so we add our 5. The next line states that y plus dy is equal to 2x squared multiplying 2 into the bracket plus 4x dx plus 2 dx all squared. Okay, and then 5 follows. Alright, and so we have that y plus dy is equal to 2x squared plus 4x dx okay, and plus 2dx all squared, 2dx all squared plus 5. Alright, and so the next step means that we'll subtract the original equations from both sides. Subtract the original equation, and the original equation was given as y to be equal to 2x squared plus 5. Okay, and so we subtract. That means from the y side we will subtract y, okay, and then from the x side we will subtract 2x squared plus 5. Okay, then we'll subtract 2x squared plus 5. Okay, and so we have y takes care of y, and so we are left with dy, and then we have 2x squared plus 4x dx plus 2 dx all squared, okay, plus 5 minus 2x squared. Minus is going into the bracket, and then minus times plus gives minus 5. Alright, and at this point dy is equal to 5 minus 5 will go 2x squared minus 2x squared goes 2, so you have 4x dx plus 2 dx all squared. Alright, so that at this point we take dy dx of this, okay, that is where you have the word dy dx coming. Okay, and sorry I didn't explain to you that when we talk about differentiation we talk about areas under a slope, because when we use dy dx we wanna dx, okay, will as well be equal to, on this part we have dy dx, okay, and dx plus 2 dx all squared over dx. Okay, this takes care of this, and then we have that dy dx will be equal to 4x and a plus, this takes care of this, and then we have 2 dx. Alright, but if x dx tends to 0, if dx tends to 0, this dy dx will be equal to 4x, and this becomes 2 times 0, and so dy dx is equal to 4x. Alright, so therefore the derivative of that function dy over dx is equal to 4x. Alright, and before we go into further solving, I want to say something about derivatives. There are other methods for derivatives. There is the binomial method for finding your derivatives, and we would like to use the binomial method for finding derivatives. Binomial method for finding derivatives. Alright, binomial method is a simplified way of carrying out expansion of number, carrying out expansion of numbers. Alright, and so for this binomial method of expansion we'll be considering some little illustration before we go into that of differentiation. Alright, remember that in differentiation we try to differentiate numbers of the form y equal to x raised to the power n. Okay, and making it easier, the binomial expansion states that this could be easily be determined by doing this n x n minus 1, and dy dx of this implies that if you are given y equal to x raised to the power n, okay, the binomial method suggests that you bring down n, okay, and then you have x, and then you subtract n1 from n. Okay, so that means that for the last example we did, okay, where we were given y equal to 2x squared plus 5, y equal to 2x squared plus 5, okay, and having the knowledge that the differentiation of a constant is equal to 0, dy dx is equal to the number we have here, just like here, is 2, and then we have a constant 2. It is left, you bring it down, you bring down the 2, okay, and then you have your variable x raised to power n minus 1, okay, n here represented by 2, okay, you have 2 minus 1. Alright, so we shall use any to replace all of the any on dy dx to obtain the value, and then you add plus 0 because differentiating a constant value gives 0, and so this is 2 times 2, you have 4, and then you have x 2 minus 1, okay, plus 0, which is equal to 4x, and the same thing we had as our dy on 1. Just look at 1, it's the same value. Alright, so we shall go on to describe the binomial method of expansion. The binomial method of expansion is given as follows. Binomial method of expansion is given as follows. Alright, this method states that if you have two values you want to expand, alright, such that if you have two values like a and b, okay, raised to the power of anything, and you want to expand them, okay, you can simply do this expansion by saying a raised to the power n, okay, while b raised to the power 0, okay, and then plus you can say n combination 1. I believe you must have done something on combinatorial theorem, sorry, a raised to power n combination, and then we have a raised to power n minus 1, and then b raised to power 1, and then plus n combination 2. You can as well write this as n combination 0, but n combination 0 is always 1, and then you have a raised to power n minus 2, and then b raised to the power 2, and this continues till we get to a point where we get n combination n being the last number, and then a is raised to the power n minus n, which will give 0, and then b will be raised to the power n as the last number. Alright, and take an illustration to show this. Example, if we are given a plus b raised to the power 2, okay, or let me use 4 because 2 we already know the outcome of 2, and so this becomes n, where n is equal to 4 combination 0, and a is raised to the power 4 while b is raised to the power of 0, and then n combination 1, a is raised to the power 3 because a reduced by 1 because we have 4 minus 1 gives you 3, and then b is raised to the power 1, and then for n combination 2, a is raised to the power 2 because n minus 2, which is 4 minus 2, gives you 2, and b is raised to the power 2, and then we continue till we get to the last number n, which is 4. I'm changing all my n to 4, all my n's to 4. Alright, and then 4 combination 3, and a is raised to the power 1, and b is raised to the power 3, and then plus 4 combination 4, and then a is raised to the power 0, n minus n, 4 minus 4, and then b is raised to the power 4. Wow. And so we have 4 combination 0 to be equal to 1. I'll show you how that is obtained. A raised to the power 4 and b plus 4 combination 1. Combination is given as n combination, capital N combination, small n is given as n factorial all over n minus 1 factorial, okay, all over n minus 1 factorial, and then small letter n factorial. Okay, if this will confuse you, why not use c? You can use c to denote the subscript there, and then you have n factorial, and then you have n minus 1 factorial, and then you have c factorial. Alright, and so if we say 3 combination, then you have this n for factorial. You know, n has to do with the numerator, and then the small b is equal to the small subscripts. Okay, so for combination 1 is equal to big N for factorial, and then big N for minus 1 factorial 1 factorial. Okay, 4 factorial is given as 4 times 3 times 2 times 1, and as depicted here, and 3 times factorial is given as 3 times 2 times 1. Don't worry, when you go over to a higher level you'll learn this. And so you have this over this, and then 3 times 2 times 1 cancels out, and then you have 4. And so we can go back and replace our 4 factorial. This one is a raised to the power 4, b raised to the power 0 is 1, plus 4 combination 1 is equal to 4 a raised to the power 3, b raised to the power 1. Okay, so go back and do for 4 combination 2. In combination 2 you have 4 factorial all over 4 minus 2 factorial and the 2 factorial, and this gives us 4 times 3 times 2 times 1 all over 4. This is 2 factorial 2 factorial. 2 factorial can cancel from this point, and then you have 4 times 3 is 12 over 2 factorial is 2. Okay, 12 divided by 2 gives us 6. And so we have that for combination 2 is 6, a squared b squared plus 4 combination 3. And for combination 3 we have as follows: 2 for 4 combination 3, and we can just do it here, and then we have
and so for 4 combination 2, we have for combination 2 to be equal to, just like stated above, we derive to be equal to 6. So we can write for combination 2 equal to 6a squared b squared 4. Alright, for 4 combination 4, we have 4 factorial all over 4 minus 4 factorial. Okay, all over 4 factorial. Alright, this gives us 4 factorial all over 0 factorial all over 4 factorial, and this takes care of this, and it's equal to 1. Alright, for combination 4 is equal to 1. A not b raised to the power 4. And then what have for combination 3? For combination 3 we have to be equal to 4 factorial all over 4 minus 3 factorial and 3 factorial. Alright, we have 4 factorial all over 1 factorial 3 factorial, which is equal to 4 times 3 times 2 times 1 all over 1 factorial is 1, and this is 3 times 2 times 1. This takes care of this, and then we have 4 to be the outcome. And so we can write 4 a raised to the power 1 b raised to the power 3, and then we can simply conclude this as a raised to the power 1 times 1 is 1 plus 4a cubed b plus 6a squared b squared plus 4a b cubed plus a raised to the power 0 is 1, so 1 times 1 is 1, so we have b raised to the power 4. Alright, so this is simply how you can expand quotients, powers, and then have it simply expressed in this form. Now what if we try to go by the long division method? Okay, where we have that a b raised to the power 4. Let's see whether we have the same thing. If you can write as a plus b times a plus b times a plus b and then times a plus b. Alright, we'll multiply these to the first two brackets. We'll have a squared plus 2ab plus b squared. Alright, again when we multiply the two last brackets to have a squared plus 2ab plus b squared. Alright, and so we'll multiply the two brackets together. A times a gives a raised to the power 4. The powers we just add indices. A times 2ab will give us plus 2a raised to the power 3, the powers will add b, and then a times b squared will give us a squared b squared. 2ab times a will give us 2a cube b. Okay, 2ab times 2ab will give us 4a squared b squared. Alright, and then 2ab times b squared will give 2a b cube. Alright, plus b squared times a squared b is b a squared b squared. Then plus b squared times 2a gives 2ab squared. Sorry, ab raised to the power 3. Okay, then b squared times b squared gives b raised to the power 4. Alright, at this time we'll have to pick like terms. We have a raised to the power 4, and then we have to a cube b to a cube b. These two can join together. These two can join together to give plus 4a cube b. Right, and then this side we have a squared b squared. We have a squared b squared here too, so we can write as 2a squared and b squared. Okay, and so at this point we have 2a squared 2a b cube, and here we have 2a b cube, can write as 4ab cube. Okay, and then at this part too we have 4a squared b squared. Okay, and then the last that followed b raised to the power 4. Alright, I think we can find a space up there, or then let's write below. Have a raised to the power 4. We can add a squared b squared, and so we have plus 4a cube b, and then plus 6a squared b squared, and then plus 4ab cube, and then plus b raised to the power 4. I think you can see that the outcomes we have here are different from what we have here too. So whether you go by long expansion method or you go by binomial expansion, you will have the same outcomes. You will have the same outcomes as we've shown here. And so we will adopt the binomial method of expansion, as the method of expansion we'll be using in our differentiation. Alright, we will only apply binomial expansion once, so that we can be able to obtain the general expression for derivatives. General expressions for derivatives. And so how do we get a general expression for derivative? We have previously said that derivatives are given as y most times x raised to the power n. Okay, these are the expression that we use for derivatives. And so what if we are told we want to differentiate this by first principle? Alright, by first principle, all we have to do is to add a little change to y. Okay, and then it affects a little change to x raised to the power n. Right, and then at this point we have to expand this x raised to the power n. And so how do we expand x plus dx raised to the power n? There is no way we can do this by method of expansion if not by binomial expansion, where we have that n combination 0, a is raised to the power n and b is raised to the power 0, plus n combination 1, n is raised to the power n minus 1 and b is raised to the power 1, plus n combination 2 and a is raised to the power n minus 2 and b is raised to the power 2, plus n combination 3 where a is raised to the power n minus 3, and b is raised to the power 2. Okay, and so it continues that way, till we get to a point where we have n combination n, and a is raised to the power of n minus n, and b is raised to the power n, And so why we stopped here is that the 3 can be enough for us to resolve what we have in mind. And so the next slide follows. N combination n, and n combination 0 is always 1, a raised to the power n and b raised to the power 0 is always 1. Alright, so what of n combination 1? Let's do it here. N combination 1 is giving us n factorial over n minus 1 factorial and then 1 factorial. Okay, this is as good as saying n factorial over n minus 1 factorial. And you know what happens with our combination with the n factorial? The n factorial keeps expanding itself, okay, so that it can be able to cancel out its denominator. So you have this, and n is out. So we have this as n a raised to power n minus 1 b raised to power 1. Okay, what about n combination 2? N combination 2 is giving us n factorial minus n minus 2 factorial and 2 factorial, and this gives us n into n minus 1, n minus 2, and we'll get to n minus 2 is stopped because that is where the numerator can cancel out the denominator, and you have n into n minus 1 all over 2. Because 2 factorial is 2 times 1, which is 2. Alright, n minus 1 all over 2. And so we bring a raised to power n minus 2 and b raised to power 2. And so we do for n combination 3. We do for n combination 3, and so we have as follows. Go over to the next slide. We have n combination 3 to be equal to n factorial over n minus 3 factorial and 3 factorial. Alright, and this expands n minus 1, n minus 2, n minus 3 all over n minus 3 factorial, 3 factorial, and this takes care of this. 3 factorial is equal to 3 times 2 times 1, 3 times 2 is 6, and so we have n into n minus 1, n minus 2 over 6, and it continues in that format. Alright, and so we have n minus 1, n minus 2 over 6 a raised to power n minus 3 b squared. Okay, and then when it continues and gets to the last point here, n combination n will give us 1, a raised to power n minus n will give us 0, and then b raised to power n. Alright, so we have done this expansion. So all we need to do now is to replace it back into our equation. Okay, so we can say that y plus dy is equal to this. Okay, y plus dy is equal to the expansion we have here. So therefore we can say that y plus dy is equal to a raised to power n, because that is the only thing that will come out here. Then n into a raised to power n minus 1b plus n minus 1 over 2 a raised to power n minus 2 b raised to power 2 plus n minus 1 n minus 2 all over 6 a raised to power n minus 3 and b raised to power 2 and plus b raised to power n. Alright, so we'll stop at this point, and so so just like we always do, y plus dy minus y. Okay, we subtract the original equations, okay, which is equal to a raised to the power n, okay, plus n of a raised to the power n minus 1 b plus n into n minus 1 over 2 a raised to the power n minus 2 b squared plus n minus 1 n minus 2 over 6 a raised to the power n minus 3 b squared, alright, plus the total lines, and then b raised to the power n. Okay, I just want you to make some adjustments. I think we have successfully expanded for a, okay, and that's x and dx. Okay, so all we have to do is we can say let's we expanded for a plus b and raised to the power n, and so we can now say let a be equal to x and then b be equal to dx. So wherever we see a, we replace as x, and then wherever we see b, we replace as dx. Alright, so we can say that y is equal to x raised to the power n, x raised to the power n plus okay, n of x raised to the power n of x raised to the power n minus 1 dx. Okay, we're replacing, and then we have plus n. Alright, let me go back so I can see clearly. We have n minus 1 over 2 is power. We have n minus 1 over 2, and then we had a raised to the power, that is x raised to the power n minus 2, and dx x to the power 2. Then we have n minus 1 n minus 2 over 6, and then we have we had x raised to the power n minus 3 and dx raised to the power 3. Okay, I think that's the 4 we had. Okay, and the x raised to the power 3, right? And so we said it continues until the x is raised to the power n. Fine. So this is our dy now. So we can say that, okay, this is our dy, representing this in y plus dy. Okay, so that we can say that y plus dy minus y will be equal to x raised to the power n plus n of x raised to the power n minus 1 dx, okay, plus n into n minus 1 over 2 x raised to the power n minus 2 dx all squared, plus n to n minus 1 n minus 2 over 6 x raised to the power n minus 3 dx raised to the power 3. Okay, then plus to here we have that dx is raised to the power n, then minus y is the original equation, this, okay, x raised to the power n. Alright, so y, this y takes care of this y, x raised to the power n here takes care of x raised to the power n, so that dy is equal to n of x raised to the power n minus 1 dx, okay, plus n minus 1 over 2 x raised to the power n minus 2 dx all squared, plus n into n minus 1 and n minus 2 over 6 x raised to power n minus 3 dx raised to power 3. Okay, and then it continues to have dx raised to power n. Fine. So that dy dx will be equal to mx raised to power n minus 1 dx all over dx plus n minus 1 over 2 x raised to power n minus 2 dx squared all over dx, then plus n minus 1 n minus 2 over 6 x raised to power n minus 3 dx raised to power 3 all over dx, and then it continues to have dx over raised to power n all over dx. And so this takes care of this, and we are left with nothing, and then this takes care of this, and we are left with 1, and then this takes care of this, and we are left with dx raised to power 2, and then this takes care of this, and we are left with dx raised to power n minus 1. Right. So the outcome for the y dx will equal to nx n minus 1 plus n into n minus 1 dx, sorry, n minus 1 to x raised to power n minus 2 dx, okay, plus n minus 1 n minus 2 all over 6 x raised to power n minus 3 dx all squared, and so it continues to have dx raised to power n minus 1. And so at this point, if dx tends to 0, so we have dy dx to be equal to n x n minus 1 plus n minus 1 x raised to power n minus 2 times 0 plus n into n minus 1 n minus 2 all over 6 x raised to power n minus 3 dx, sorry, 0 squared, and then we have plus 0 raised to power n minus 1, and so this gives 0, and then 0 times the whole of this gives 0 too, and then this gives 0, so we are left that dy dx is equal to n x n minus 1. So therefore, if y, the derivative, is equal to x raised to power n, dy dx will be equal to n of x n minus 1. Alright, we'll try to use this to find some derivatives. We'll be using this to differentiate numbers quickly so that we'll find their derivatives. Alright, for example 1, we are told to differentiate this, differentiate y equal to minus 4x squared plus 7x minus 2, right? Now solution. Okay, the solution has it that solution 1 has it that knowing that if y is equal to x raised to power n, that dy dx is equal to n x n minus 1. Okay, so all we have to do, also you have to note that the derivative of a constant, okay, k is equal to 0. Alright, and so for y equal to minus 4x squared plus 7x minus 2, we can say that dy dx is equal to we have n. Okay, so n for 4 is 2, and so you have to bring down 2 and then leave 4 the way it is. And for the x, we have to subtract 1 from the x, power of x. Okay, the same thing happens to 7. We have to bring down the power of x in 7, and the power of x in 7 is 1. Okay, we leave 7 where it is, and then we subtract 1 from the power of x in 7. Alright, for 2 we'll just write 0 because the derivative of a constant is equal to 0. And so we have 2 times 4, we have minus 8, and then x, because 2 minus 1 gives you 1. So we don't normally write the 1, so we leave it as minus 8x plus 1 times 7 is 7, and then we have x raised to power 1 minus 1 x 0, x raised to power 0. Okay, and this one is gone, which is equal to minus 8x plus 7, because x raised to power 0 is equal to 1. Alright, so if you follow the other method of finding derivatives, you will find out that this method is the same. You will get the same outcome. Alright, we have managed to find the short form, or a short way of differentiating numbers. At this point in time, we will have to state some standard derivatives that will be helping us to differentiate functions. Okay, so all we have to do is to state them. They have proofs too, but we wouldn't go into proving them. They will be for higher levels of mathematics, and so we're just going to state in the formulas and then applying 1 or 2 of them. Okay, I want to use a table to represent them. Alright, so if here we stand for my y variables, let me make the table look better. So we have a table, we have y here. If y is equal to x raised to power n, as we said earlier, and then what would dy dx be? Equal to x raised to power n minus 1. If y is a constant, dy dx is 0, and then if y is a x raised to power n, dy dx is n of a x raised to power n minus 1. Okay, and then if y is a trigonometric function sin x, then dy dx is cos x. Okay, and then if y is cos x, dy dx is minus sin x. Okay, and if y is tan x, okay, dy dx is sec squared x. Alright, and if y is x exponential x, dy dx is exponential x too. And if y is a multiple of two functions, dy dx demands that you differentiate the second function with respect to the first function, and then the first function with respect to, you keep the second function constant and differentiate the first function, and then you add the differentiation of the second function keeping the first function constant. We'll do examples on that. What if the two functions are guided by division u over v? Okay, you keep the first function constant, differentiate the second one, you keep the denominator constant, differentiate the second one, and then you keep this constant and differentiate the denominator all over 2. Alright, all over v squared rather. We'll carry out examples on this, and then you will understand better what we mean. For now, go and practice this so that In the next class, you can follow along. Have a nice day. Bye.